Look up at the night sky. What do you see? A vast, dark canvas, sprinkled with countless points of light. Each one is a distant sun, a star. For thousands of years we have gazed at these stars, told stories about them, and used them to find our way across oceans. We've always thought of them as solitary travelers, each star moving alone through the immense emptiness of space. Our own sun seems to confirm this idea. It's the single blazing heart of our solar system, with only planets for company, a lonely giant in its corner of the galaxy. But what if this picture is wrong? What if the idea of the lonely star is just a myth? The universe is often more complex and, honestly, more connected than we first imagine. We are learning that many stars are not alone at all. They have partners. Imagine a universe where most stars have a partner. This is the reality that modern astronomy is revealing. A binary system is simply two stars that orbit a common center of mass. They're bound together by gravity, circling each other in a celestial dance that can last for their entire lifetimes. Think of it like a cosmic waltz, two giant balls of fire spinning through space together. This isn't a fringe phenomenon, it's incredibly common. In fact, more than half of all the stars like our Sun are thought to be in binary or multiple star systems. When we look up at what appears to be a single star, we might actually be looking at two, or even more. Our eyes simply can't tell them apart from such a great distance. The night sky is filled with these hidden duos. Each one is a unique system with its own story. Some pairs are close, orbiting each other rapidly. Others are far apart, taking thousands of years to complete a single orbit. A star with a companion evolves very differently from a star that is alone. The constant gravitational pull from its partner can change its shape, its size, and even its lifespan. The two stars can exchange material, with gas flowing from one star to the other. This interaction creates situations and phenomena that are simply impossible for a single star to experience on its own. What happens when this cosmic dance goes wrong? The gravitational embrace that holds a binary system together can also lead to its doom. Stars in a binary system do not live forever. Like all stars, they evolve, they change, they grow older. As they do, their orbits can change too. They can get closer, and sometimes they get too close. The delicate balance is broken, and the two stars are set on a collision course. This is not a gentle merger. It is one of the most violent and energetic events in the entire universe. Two stars, each a colossal nuclear furnace, smashing into one another. The energy released is almost unimaginable. It is a cosmic cataclysm. The collision rips the stars apart. It triggers runaway nuclear reactions. It creates a burst of light so bright it can outshine an entire galaxy for a short time. For a moment, this single point in space becomes one of the most brilliant objects in the universe. The result of a star collision is a brand new object. The two stars merge to become one much larger star. Or the collision can be so violent that it triggers a massive explosion, a supernova. This explosion scatters the elements that were once locked inside the stars across space. These elements, like carbon, oxygen, and iron, are the very building blocks of planets and of life. In this way, the death of two stars in a fiery collision can seed the cosmos with the raw materials for new beginnings. It is a powerful example of the universe's cycle of death and rebirth. The graceful looping dance of a binary star system is not random. It is governed by one of the most fundamental forces in the universe, gravity. Over 300 years ago, Sir Isaac Newton formulated the laws of motion and universal gravitation. These laws describe precisely how two objects, in this case two massive stars, will pull on each other. Each star follows a specific path, an ellipse, around the system's common center of mass. This is the very heart of how binary systems work. The shape and duration of these orbits can vary enormously. Some are nearly perfect circles, while others are highly elongated ellipses. The time it takes to complete one full orbit, known as the orbital period, can range from mere hours for the tightest pairs to many thousands of years for the widest ones. By carefully observing the dance, by measuring the size, shape, and period of the orbits, astronomers can work backwards. They can use Newton's laws to calculate one of the most important properties of a star, its mass. The simplest type to understand is a visual binary. These are pairs where the two stars are far enough apart and close enough to Earth that a powerful telescope can actually see them as two separate points of light. One such method reveals what we call a spectroscopic binary. We use an instrument called a spectroscope to split the starlight into its rainbow of colors. By seeing the light shift back and forth, we know there must be two stars there, locked in a tight, fast orbit. Another fascinating type is the eclipsing binary. From our perspective, one star periodically passes in front of the other. When this happens, it blocks some of the light from the star behind it, causing the total brightness of the system to dip. A star in a binary system does not live its life in isolation. Its entire existence, from birth to death, is profoundly influenced by the constant presence of its companion. Imagine two stars born at the same time, one significantly more massive than the other. The more massive star will race through its life, burning brightly but quickly. It will be the first to swell up into a red giant, a huge bloated star in its old age. As it expands, its outer layers can reach so far out that they begin to feel the strong gravitational pull of the smaller, less evolved companion star. This is where the story takes a dramatic turn. The companion star can start to pull gas and material away from the giant star. A stream of glowing matter can form between the two, a process known as mass transfer. This mass transfer can completely alter the destiny of both stars. The star that was once more massive can lose a significant amount of its material, effectively putting the brakes on its evolution and extending its life. Meanwhile, the smaller star, which was destined for a long, quiet existence, suddenly gains a huge amount of new mass. Most importantly, the added mass can dramatically accelerate its own evolution, pushing it towards a much earlier and more violent end. A crucial concept in understanding this balance is the Roche lobe. You can think of the Roche lobe as a teardrop-shaped region of gravitational influence around each star. The two Roche lobes meet at a single point between the stars, a gravitational saddle point known as the inner Lagrangian point. This is the gateway through which material can pass from one star to the other. Once the star's surface reaches the edge of its Roche lobe, any further expansion means its outer layers are no longer gravitationally bound to it. The material spills over through the Lagrangian point and begins to fall towards the companion star. Binary star systems are far more than just a cosmic curiosity. They are one of the most important tools astronomers have for understanding the universe. They function as unique, natural laboratories. By studying the precise, predictable orbits of binary stars, we can directly measure the most fundamental property of a star, its mass. This is the bedrock of stellar astrophysics. Binary systems are also responsible for creating some of the most exotic and energetic phenomena in the cosmos. These X-ray binaries are beacons that help us find and study these otherwise invisible stellar remnants. For thousands of years, stargazers have watched the constellation of Perseus. Within it lies a peculiar star, one that seems to misbehave. The ancient Arabs named it Algol, which translates to the demon star. Algol is not one star, but two. It is an eclipsing binary system. The demon star is a perfect, real-life example of a stellar partnership in action. The solution to the paradox lies in the interactive nature of binary systems. Originally, the orange star was the more massive of the two. Over time, the roles were completely reversed. Algol is not a demon. It is a witness. In 2008, astronomers were observing a star in the constellation of Scorpius, catalogued as V1309 Scorpii. The two stars were whirling around each other faster and faster, spiraling inwards towards their doom. Then, in September 2008, it happened. The two stars had finally merged. They had collided and exploded, just as the theories predicted, producing a classic luminous red nova. For the first time, we had a complete record of a stellar merger event, from the final inward spiral to the climactic explosion itself. It was a stunning confirmation of our models and a landmark moment in astronomy. For very close binary systems, one of the main drivers of this decay is the emission of gravitational waves. As these two massive objects whirl around each other, they disturb the very fabric of space-time, sending out ripples of gravity that travel across the universe. Another powerful mechanism for orbital decay happens in contact binaries, where the two stars share a common atmosphere. This shared envelope creates enormous friction and drag. It acts like a brake, slowing down the orbital motion of the two stellar cores buried deep inside. The journey towards collision is a one-way street. Each rotation brings the stars closer. The closer they get, the stronger their gravitational interaction becomes. This, in turn, can accelerate the decay process. As the two stars spiral closer and closer, they reach a critical stage. This is the point of no return. The stars begin to physically distort one another in a process known as tidal disruption. The tidal forces become so extreme that they start to rip material from the surfaces of the stars. Great streamers of incandescent gas, each one larger than a planet, are torn away and flung into the space between them. This stage is incredibly short-lived. While the initial orbital decay can take millions of years, this final violent phase can be over in a matter of hours or even minutes. Eventually, the inner edges of the distorted stars touch. This is the moment of impact. The point of no return has been passed, and the collision begins. The moment the stars collide, all hell breaks loose. The initial impact triggers a runaway thermonuclear event. This unleashes a titanic burst of energy in a very short amount of time. The combined mass of two stars erupts in a single, colossal explosion. For a brief period, the light from this one event can be astonishing. It can outshine all the other hundreds of billions of stars in its galaxy combined. On the 17th of August, 2017, a new era in astronomy began. Detectors on Earth, one in the United States and one in Italy, felt a tiny tremor in the fabric of reality itself. It was the unmistakable signature of two neutron stars, the ultra-dense corpses of massive stars, spiraling into each other in a final, violent dance. Just 1.7 seconds after the gravitational waves arrived, space-based telescopes detected a powerful, short burst of gamma rays from the same patch of sky. This was the smoking gun. In the hours and days that followed, telescopes all over the world turned to look at the location of the signal. They saw something incredible. A new point of light had appeared, one that had not been there before. This was the first ever observation of a kilonova, the radioactive afterglow from the debris ejected during the neutron-star merger. By analyzing the light from this kilonova, scientists could see the spectral fingerprints of elements like gold, platinum, and uranium. We now have direct evidence that they are synthesized in the unimaginable heat and pressure of a neutron-star collision. The gold in a wedding ring, the platinum in a catalytic converter, these precious materials were forged in a cataclysmic event like GW 170817. This single event, observed through both gravitational waves and light, has revolutionized our understanding of physics, stellar deaths, and the origin of the elements that make up our world. The story of the universe is not written in isolation. It is written in the interactions between these stellar partners. We are, in a very real sense, the children of past stellar cataclysms. Our journey into the world of binary stars is far from over. In fact, we are standing on the cusp of a golden age of discovery. Each new generation of telescopes and detectors brings the hidden universe into sharper focus. In space, missions like the European Space Agency's Gaia satellite are already creating a revolutionary three-dimensional map of over 1 billion stars in our galaxy, uncovering hundreds of thousands of previously unknown binary systems. Looking even further ahead, future space-based gravitational wave observatories like LISA will be able to detect the gentle, low-frequency ripples from wide binary systems long before they merge, giving us an early warning system for cosmic collisions. So what does all this mean for us, here on our small blue planet orbiting a single solitary star? The story of binary stars and their collisions is not just some distant, abstract astronomical curiosity. The very atoms that make up our world, our bodies, and the air we breathe were forged in the hearts of stars. And it is the violent interactions and mergers within binary systems that play a crucial role in scattering these life-giving elements across the galaxy. We are, in a very real sense, the children of past stellar cataclysms. Our existence is built upon the ashes of long-dead stars. The next time you gaze at the stars, remember the hidden dances taking place. Remember that many of those single lights are actually partners, locked in a gravitational embrace. Their shared story might be one of quiet companionship, Or it might be a countdown to a spectacular collision that will forge new elements and reshape a small corner of the galaxy. The lonely star is an illusion. Everything is linked in a grand cosmic web of cause and effect, a story of shared destinies and violent creative transformations. The cosmos is more alive, more connected, and more wondrous than we ever dared to imagine.